All right, so here's what I was picturing, is that since the test is a week from today, that we're gonna do a lab today, and Thursday will be class for you. I figured there'll be more questions on Thursday than today, considering the test. This is my thinking. If I'm completely wrong, we can call an audible here and change it. But the plan is to do a lab today. But we'll start out with any questions or comments. And I'll throw in that the lab today is due not a week from today, but a week from Thursday. Because you have a test next Tuesday, and so I don't want you to have to worry about getting this in. Yes, Olivia.
Had a question how to find like the speed of an electron as it transfers from two parallel plates.
Yep. Oh, there it is. I give you the potential difference. What information do I give you on that?
I think we're supposed to.
Let's see, that would be 19.
Yeah.
What are the chances I have a copy sitting right here? Apparently a poor chance. Anyone have the chapter 19 master set? Ah, thank you. Question 4. Parallel plates, capacitor situation, should I give you the size? The gap between them. The important thing about the size and the gap between them is the gap between them is significantly smaller than the dimensions of the plate. So therefore we can make the assumption of infinite sheets. I give the charge, we go through, we find the electric field, and then down to the end, so it's the last two parts, right? Okay. So if I have two plates here, I got a positive plate and a negative plate, and I put an electron here, which way will it go? Okay. And we have 4 different explanations for that. So let's just run through them quickly. From a force point of view, why does the electron go to the left?
Opposites attract
And,
lights repel.
right, yeah, there's 2 sides of it. It's being pulled and pushed. All right, from which way is the electric field going?
From the positive to the negative.
Yep. So there's my electric field. So from an electric field point of view, why does the electron go that way?
It's charged. It's charged.
Yeah, but why does its charge make it go that way?
Because it's the force per unit of charge, and it will want to be moving. The electron will be making a change to move in the opposite direction of the positive charge.
Close. The negative charges go upstream. They go opposite direction of the electric field. Because if I have an electric field right here, that's an electric field right there, and I put an electron into it, the electron's gonna go that way. And I don't know what causes this electric field, it doesn't matter. I just know negative charges go opposite direction of the electric field. From a energy point of view, if I put an electron there and I let go, what's gonna happen?
potential?
Since the electric force is conservative, if it goes to a higher potential, I say potential energy, what happens to the kinetic? It would have, okay, I see some people making hand gestures there. What's the problem?
We need to be the other way around.
Yes. If I put this here at rest, its kinetic energy is 0, it suddenly starts to move, therefore the kinetic energy increases. And because the electric force is conservative, potential energy must decrease. And so potential energy decreases as opposite charges get closer to each other or as like charges get farther apart. So that's from the energy point of view, and that's a key one for this particular problem. And then from an electric potential point of view, not energy, but electric potential, which way do negative charges flow? This might have been what Ian was thinking about.
From high potential energy to low potential energy?
That's positive charges. Negative charges go
From low to high.
low to high potential. All right. And the positive plate is a higher potential than the negative plate, and so it's going to move from a low potential to a high potential. All right, so the energy one is the key one in this particular case. I know that energy is conserved. So my E initial is equal to my final energy, which is equal to, so I have K initial plus U initial is equal to K final plus U final. I know my initial kinetic energy is 0, because I believe the electron starts at rest. You're looking at me questioning.
Yep.
Yeah, okay. So my initial kinetic energy is 0. So which of these deals with how fast it's moving?
Kinetic energy?
Yeah. Oh, let's do this. We can do it. What's the formula for kinetic energy?
1/2 mv squared.
That was nice. And then if I subtract potential from the final potential energy from both sides, I end up with Ui minus Uf. So this is just the negative change in potential energy. And so we have to figure out what is that change in potential energy. Well, for the case of an electric force, what is the potential energy formula? It's sort of a red herring here, but you should know it anyway.
KQ over R.
That's the electric potential. The electric potential energy has one extra term in there.
Oh, KQ1, Q2
Yeah.
over R squared.
Ooh, no,
Oh,
too far.
over R.
Over R. Over R squared makes it the force.
The force.
All right, so we have our electric potential energy formula right here. However, this works for point charges. It doesn't work for parallel plates. So we got another thing that we have to worry, that we can deal with here. Going to what was just said there, the electric potential, that's KQ over R. The difference between them, not in the mathematical sense of difference, is the extra charge here that's not here. So we have one other relationship here, that the change in potential energy is equal to some charge that's going through a change in electric potential. Therefore, that I believe you know, that's the potential difference between the plates, or the voltage. Q would be the charge of the electron, and then that will tell you the change in potential energy. Once you know the change in potential energy, you can find the speed. Does that answer your question?
Yes.
Okay. Other questions about this or others?
had a question about the conceptual problems.
Yes?
So for 28, we're trying to show and justify the configuration of the signs of corner charges. And I got the stable one, but I'm confused about what the charges would be for an unstable equilibrium.
All right, so what was the word? Was it a specific question or?
Yeah, there's 4 point charges with one in the middle.
Okay. Show just like configuration of the signs of the corner charges with this stable, unstable, or semi-stable. Okay. So stable or versus unstable equilibrium conceptually is if I've got a charge that's in equilibrium, let's just take the simple case, the physical case of if I have a valley here and I have an object sitting at the bottom, that is a stable equilibrium, because if I give it a little nudge, it's not gonna go shooting off. It's just gonna try to come back to where it started. Stable. Unstable equilibrium, I have a hill here with a ball on top of it. It's in equilibrium, but a slight nudge and that thing is just gonna go shooting off. Unstable. So we want a situation where an object, once it starts moving in a particular direction, it will keep getting drawn in that direction. So whatever the charge configuration is, there has to be an attraction once you nudge it away. And that attraction must increase as it gets closer, which works with electric charges. So a stable equilibrium would deal with it's being repelled. The closer it gets to something, the more it's repelled. So if I had a positive, positive, and positive charge, for example, if I nudge the positive charge in this direction, it's getting repelled by this, so it's getting pushed back. This will be a stronger force because it's closer to this one. That'll be weaker, so the net force will be in that direction, so it gets pushed back to the middle. It's gonna cross that threshold and then be pushed, and then suddenly this is the dominant force, and it keeps getting pushed back and forth. So unstable would be, I give it a little nudge and it is attracted.
Okay.
Is that sufficient for now? Except, I mean, you got 4 corners there, but I think you
Yeah.
can work it out.
Yeah, thank you.
Yep. Other questions?
Master said 20 is due next Tuesday, which the test is due.
Master said
20.
20? Oh, yeah, we'll push that off to Thursday, if that works for you. That means you'll have 2 things to do that Thursday. I'm probably not gonna change the due date in Blackboard, but just know. I noticed that at some point, then I forgot to mention anything. All right, I want to do a little bit of a prologue on the background for what we're going to be doing in lab. You've gone through the master set some more academic aspects of the dielectric and the parallel plate capacitors. So we're going to have what are called simple form capacitors, and they're just basically, well, it's a piece of metal that is sort of bent like this. And then there's going to be a connection here so that you can connect it to some sort of small little power supply. One side will be positive, one side will be negative. Just out of habit, or put the positive side on the left, it's not necessarily going to be. And we have an electric field going across like this. Then when you put a dielectric in between it, if this is hooked up to a battery, positive side, negative side. Hooked up to a battery, you've got the electric field going across like that. I put in a dielectric. Dielectric, by definition, has to be an insulator. If it were a conductor, then you couldn't build up any charge. Matter of fact, what will happen is if you are testing the capacitance here, if there is a connection, what the meter's doing is going, how much effort does it take to put a charge onto the plate in order to build it up, or how much charge can I put on the plate? And if there's a connection, it is going to basically keep putting more, from the meter's point of view, is putting more and more charge onto it. It has no idea that it's just being conducted through. And so, from the meter's point of view, you get infinite charge on it, therefore you have infinite capacitance. But in fact, you have zero. The meter doesn't know. So this has to be an insulator. And what's happening is I've got an electric field coming from the plates here. And in the dielectric, because I have a electric field and an electric field coming across, it's going to polarize the molecules inside the dielectric. So the little molecules inside here will start to reorient, and you'll tend to get the negative on this side and positive on that side. Now, we're not having the negative charges flow over there because it's not a conductor. They're still rather tightly bound to the atom or to the molecule itself, but things will polarize, and because of that, you get all these electric fields going back in the other direction. And that's what lowers the overall electric field between the plates. And so we're gonna be doing it, we'll have the parallel plates, we're gonna use paper as an insulator, copy paper, and you're gonna start out with a couple sheets and then slowly build up to 3 through 12. I'd have to, oh, I have it right here. 3 through 10 sheets in it. And as you put more and more sheets in there, you'll be separating the plates a little bit more. The capacitance will change because, well, the capacitance, epsilon naught, kappa, A over D. I'd have to think through that, I think that's right. Otherwise I'd have to think. I'm going off memory. Let's see, if the distance increases, the capacitance drops. As the area increases, capacity, okay, feel better. This right here is a dielectric constant. It is a kappa, not a K, and ultimately you're going to be trying to find that value. Through the beauty of a graph. So the first part is you're going to be putting paper in between it and changing the distance in between. Now, one of the issues that you will find is that these plates here are not perfectly designed. It's not a perfect right angle, much like my house. So they're slightly warped one way or the other, so we need to keep the two plates pressed together. We can't just set them up, put the paper in between, and be satisfied with it. We need to somehow get them clamped together. And so I guess when we get in there, I'll talk about that, because there's some mechanics involved. And the second part is we're going to test inverse area, so we'll have the two plates side by side with, I think it's 4 sheets, whatever the lab says, and then we'll slowly start shifting the plates apart like this. And so the overlapping area gets smaller and smaller as we go, and so the capacitance should drop because, in essence, what I care about is that parallel, how much overlap is there. When you get to the end, so you're supposed to move it over, like, I think it's 2 centimeters each time. Yeah, 2 centimeters each time. In the last one, some people get a negative area, because if there's a small little bit of a gap there, and you've got a negative area, if you put down the negative area or you put down 0, I'm good either way. And I think that's all the prologue you need from here. So let's head over to the other room. Here we go.